Good morning. It's a beautiful morning here in Conroe. I've got Ellie with me. Say hi, Ellie. I've got a wonderful cup of coffee. And we've got single area OSPF to talk about. So, first, I'm going to briefly talk about RIP, what it is, kind of to give you an idea, because we're going to use it to contrast OSPF and RIP. And I want you to know at least a little bit about RIP. Then we're going to talk about OSPF features and characteristics right here. And then in 1.2, we're going to talk about packets. In 1.3, we're going to talk about OSPF operation. So, continuing on. So what is RIP? Why don't we use it? Why don't we teach it? Just briefly, it's a distance vector protocol. That means that it only pays attention to what its neighbor tells it. It only pays attention to the next hop. It only bases everything on hop count. This is a very simple protocol. It's very rudimentary. It also sends out its entire routing table constantly to all of its neighbors. I say neighbors. It doesn't really create neighbor relationships. It just spits it out all of its ports, unless you tell it not to. Very, very simple protocol. It works, but it's definitely not efficient. So comparing that to OSPF here, OSPF is a link state routing protocol. This means it actually develops a map of the entire network. So if you think about it kind of like your route to work. So my route to work is pretty simple. I usually take 3 or 4 turns to get there. I live right off of a major road. I turn onto the major road, drive for a while, and then turn off the major road onto the little road that my place of employment is. Well, so you may, like I do, there's an alternate path, another road that runs parallel to the road that I take every morning. And it's not bad. I know that, and there's been times where this is backed up, and I'll just take the alternate path. Well, you know, and I know there's other ways you can kind of get around and do some other kind of suboptimal things to get there, but you can get there. And I know a couple of those paths because I'm familiar with the area. Now, OSPF is going to know about all these different paths, whereas RIP is only going to know about the best path. And it's going to have to figure it all out again if it has to find another path. If this path goes down, if there's a major accident or something, it's going to take a lot longer to figure that out. That's why we appreciate OSPF. It's a lot more quick when there's a failure, and it's going to be a lot more efficient, as we'll see here coming up. So we have the entire network topology. We are aware of all of the routers, all of the links. We're going to know about, I just said that, all the links, the status, the subnet, which routers are connected to what routers, the cost. That's very important. We're going to use the cost to determine which path is better. So with RIP, we only understand hop count. So if there's more hops, that's bad. So you may have 2 routers that are directly connected at a 10 meg circuit, and you may have a path of 4 routers with a 10 gig circuit. So if we kind of draw this to make sense of it, so this is 10 meg. And imagine all these are 10 gig. I'm not going to put that on all of them. So this is actually a faster path here, but RIP is going to pick this one because it only has the 1 hop instead of 4. Whereas OSPF will take into account cost, which has to do with speed. We'll take speed into account here, and so we'll notice that and take the other path. Moving on. So this will give a faster convergence. I apologize. It'll do a faster convergence. And all that means is that everyone's in agreement, right? Our entire network knows all the paths to every network. That's what we want, right? That's what convergence is. So every router is going to have a full routing table. The quickest is faster, and it's going to be able to scale larger. We're talking about multiple area OSPF and how that scales in just a little bit. So we're going to use the concept of areas. Areas are going to allow us to control routing updates and limit local resource usage. And we'll talk about that in detail in just a little bit. We're also classless by design, right? IPv4 classes were invented with IPv4 back when we had like a total of 250 devices on the internet. But now we don't use that anymore, so OSPF didn't care about that. We also have authentication and encryption if we want. This stuff isn't particularly strong or very good, but it is something that if you are a very, very security conscious organization, you might want to keep in mind. RIP doesn't have anything at all. So all routing protocols are similar. They all have a similar focus to exchange routing information, right? So we're all going to have some kind of data structure, some kind of database, and we're going to have some kind of routing algorithm, even if that algorithm is literally, 1 plus 1. That gives us, a hop count of 2 for RIP. And some may be very, very complex. If you look at a routing protocol like EIGRP or BGP, those algorithms can be really, really complex and really throw you for a loop. So OSPF specifically, we're going to have 5 types of message packets we're going to worry about. We're going to have the hello packets, right? Those are going to be kind of an intro. Hey, is there anyone running OSPF on this link? I'm running OSPF. Is anyone else here? We can establish a neighbor relationship. And we're going to talk about that process in just a bit. Then we have our database description packets. It's going to say, hey, I know about 192.168.1.0/24. It's just going to give a basic description of what the router knows. Then the other router will respond with a request if it doesn't know where one of these networks are. Hey, can you tell me about that 192.168.1.0 network you told me about? I don't have the details on that, and then that will respond with details. So the database description is really just, these are the networks I know about, not any kind of details about how to get there, where they're connected on. It's just, these are the networks I know about. So very, very efficient compared to RIP. RIP just spits out all of its information all at once. Yeah, very, very more. English is not my strong suit, obviously. Very, very efficient compared to RIP. Then we have link state updates. So if there's any kind of update, anything changes, we can send those. And link state acknowledgements, which we want to make sure our messages get to the other router. It's very important because we need to synchronize all of our databases. So that is very important there. Okay, so we're going to have 3 databases that we're going to deal with here. We're going to have our adjacency database. This is going to tell us who our neighbors are, right? Who's connected to us. We can do that show IP OSPF neighbor command. Very, very useful command. I use it all the time to see what our neighbors are, who we've established a neighborship with in OSPF. We're going to have our link state database. This is going to show us a topology table. This will have all of our information. All routers will have an identical LSDB. The adjacency database is unique, and the routing table is unique. But the link state database is going to be identical. We can show this with show IP OSPF database. It's going to show us all the information we know about all of the links in the network. And then, of course, we'll have the forwarding database, which is actually what we have in our routing table, which is what we use to actually route traffic. It's going to be unique, and we're going to use the show IP route command to see that. And so the way this works is first we build an adjacency database, we talk to those other routers and figure out where every network is. Then we put that information into our LSDB. That LSDB runs through our algorithm, and then the algorithm tells us what to put in the routing table. So we're going to use the Dijkstra algorithm. The J is silent. The Dijkstra algorithm, or also the SPF or shortest path first algorithm, to determine the best path. So we're going to add up all the costs of the links. So if this link is 2 and this link is 4 and this link is 5, we're just going to add them together. It's very simple math, right? So that's 11. Very simple. It's not super complicated. a routing protocol like EAGRP is going to be much more complicated. So we're going to create an SPF tree, which, if you notice, they use the same word like spanning tree. So really, it's here's an example. That's a tree. So really, they're going to look at the network from the perspective of a router, right? So this router here, let's say it's R1. From its perspective, where's everything else? We're going to calculate every possible path. Yes, every possible path. If there are redundant paths, we're going to calculate those too. If there's 10 paths to one place, we're going to calculate all 10 paths. The best routes we're actually going to put into the forwarding database, which is used to make the routing table. Right, so if we put it in the forwarding database, then it goes to the routing table. Pretty simple. So, if you are not familiar with what an algorithm is, it's very simple. It's a fancy word that means a math equation. So we're going to have particular rules that are followed or processes in the calculation. It's just a math equation. A lot of algorithms can be really, really complicated. When you start talking about Facebook algorithms, when you start talking about algorithms, usually when people start talking about algorithms, non-mathematical people eyes just like glaze over. Most of the algorithms we're going to talk about are not super complex, and you don't have to really understand them either. You just have to understand the basics of them and how they work, not all the details of the entire algorithm. So we're going to talk a little bit about Dijkstra's algorithm here. So this works with anything. It's not necessarily OSPF. So these are just vertices. They're not necessarily routers. In our context, we're going to talk about routers. But in his algorithm, I mean, his algorithm was invented before routers existed. So kind of makes that hard. So from the perspective of this vertex, we're going to try to get to, we'll pull the example of E, right? So we can go this way. That'd give us a cost of 1 plus 1, right? Easy math, I'm telling you, you can do it. We could go this way, 6 and 2, right? So that's a cost of 8. What about this way, 6, 2, and 1. There you go. That's a cost of 9 for this one, 9. You can go this way. Right, it's the cost of 16. So OSPF is going to calculate all of these and put them into its link state database, but it's actually only going to use this link, this 2, to actually put the routing table. It's our shortest distance, right? Our shortest path first. And yes, I took this from some guy's blog. He did a great job. I want to make sure I give credit to him for this infographic here. So we're going to have these 5 routing steps here. First, we're going to establish neighbor adjacencies. We're going to use the hello packet. We're going to use our database description packet here. Then we're going to have our advertisements that are going to say, hey, you know, your LSR, your request, and your LSA, your advertisement, that tells you about those networks. The LSR requests information about a network from your database description, right? Your database description, again, is going to tell you what networks. Then if the other router doesn't have those networks, it will send a request, and then you'll send back an advertisement with all the details about that network. So yes, so we're going to build the link state database here with that information. Once we've got it all, we're going to build that link state database. It's going to have all our information in there about every single path. Then we're going to execute that algorithm on this information, and then we're going to choose the best routes that come from that algorithm, and we're going to put those actually in a routing table. I'm learning all kinds of new keyboard shortcuts with this new software I'm using to draw, so it's very, very interesting here. So we're going to exchange these hello packets between routers first. Then we're going to exchange LSAs. Those are the advertisements telling us the details of a network. It kind of missed the database description package, so that would be before that. And then we're going to create a SPF tree for each individual router. Each individual router is going to take their link state database, which should all be identical, and from its perspective, figure out the best path to everything. And you can go through these slides. I'll have them up on NetAcad so that you can review them and go through these details if you want of each individual step, but I'm not going to spend all that time. So our actual tree here, oh, nope, go back. So our actual tree here is going to tell us from R1's perspective, to get to this network, this is the best path. To get to this network, that is the best path. And here's our cost, right? Again, that's cumulative. So if we're going R1, R3, R4, R1, R3, R4, that's going to be a cost of 10 down here, 5 here, and then the 2 here, because we're actually going to 10.8. Hopefully that makes sense. If not, tell me and I'll try to explain better. So clear cursor, got it. So we can use multiple areas. We can use multi-area OSPF to increase our efficiency and scalability. So our area is a group of routers. I don't really like this definition that share the same link state information. They do. Everybody in the area shares link state databases. Really, an OSPF area is made up not of necessarily routers, but interfaces. So you may have area 0 here, and you have a router that has an interface in area 0 and an interface over here in area 1. Over here, an interface, maybe multiple interfaces in area 2. So keep that in mind, that really a router is in an area, but it isn't necessarily always in an area, if that makes sense. Let me rephrase that. Excuse me. A router is not necessarily entirely in one area. We call these routers area border routers. And we're not going to really learn, unfortunately, about some of these details. But keep in mind that these routers that are area border routers are going to have to know all the LSDB information for all the areas that they have interfaces in. So, single area. All routers are in one area. Best practice is to use area 0. If you don't use area 0, then yeah, every area has to connect back to area 0. So by definition, you're breaking all the rules. You really have to use area 0. Don't try anything stupid. Multi-area, we have to have area 0 as our backbone area. Interconnecting all of the areas together requires area border routers. And I just mentioned those briefly. So, some of the benefits of running multi-area OSPF. We have a hierarchical design, so we're going to have smaller routing tables. We're going to be able to actually summarize networks between different areas. So, it's not enabled by default when we set up areas, but we can very easily summarize. It's kind of more of a CCNP level topic, but keep in mind this is something you can do. LSUs, we're going to prevent them from going between areas, so we can optimize that because we don't need that link state database from another area. We don't have to send those updates for that other area. And then, of course, we will reduce the calculations needed because when you start getting to really complex, really large networks, there's going to be a lot of different paths you can go. So as you'll see here, at the top here, area 0 is the whole thing. It's a single area OSPF design. You have a link go down here on the right, and then it has to send an update to everybody. And this one at the bottom here, you'll see it's all split up, so only routers in area 51 have to actually get a message. OSPF v3, it's hilarious, but really the only difference is IPv6. Same functionality, same communication, same peer and advertising deal, just IPv6. Same algorithm, same computation engine, same everything. It's just IPv6. That's all. So we can run them separately, although they want you to know that OSPF v3 has an address families features, which allows you to run dual stack. That means you can run IPv4 and IPv6 at the same time. But usually we would like to have them separate. That way, if one of them crashes, the other one is still good. And that's all for 1.1. And I will create another video for 1.2. I want to kind of split these up so they're easier to digest. Maybe if you have a strict schedule or only small amounts of time, it'll be easier to get through one part, not necessarily an entire hour, hour and a half lecture. Same thing for me, because it's easier to take 20 minutes and record something and sit down, kind of regroup and do some other things before making another portion instead of sitting down for an hour and a half. So I will see you guys soon in 1.2, and we'll talk about OSPF packet types.